Let's retrieve some child records and explain how, with respect to the apply operator performance, it depends. Welcome to this video on the apply operator. My name is Kevin Fiesel, and I am the proprietor of Catalaxy Services LLC, a consulting firm which specializes in work all across the data platform space, especially SQL Server. The prior video in this series introduced ad hoc functions and the apply operator. In this video, I'll show you how we can use the apply operator to retrieve the child records we want for each parent record. Plus, I'm going to do something wildly different from my normal videos. I'm going to go to the demo first and then come back to a classroom segment. Please do not panic at this complete inversion of the norm, as I promise there is a reason for it and not simply the whims of a content creator. With that stated, let's go to the demo. Here we are in Visual Studio Code. Just like in the prior video, we'll spend a little bit of time in here, but most of our time in SQL Sentry Plan Explorer. The first example I'll show is how we can get the latest child record per parent record. In the Wide World Importers database, I'll use customers as my parent record. Before we go any further, let's see how many customers there are in the database using this query I've already put together that joins the customers table to the people table. When I run the query, I get back 735 rows. That means if I want to get the latest order for each of my 735 customers, I expect to get back at most 735 rows and possibly fewer if I use cross-apply and we have customers who do not have orders. The next thing I'll do is make sure that I have a reasonable index on the customer transactions small table. This will ensure that any queries I write will be able to use an appropriate index so that I am not unnecessarily slowing down any style of query. I'll next create a similar one on the customer transactions table. As you might guess, the small table is a subset of the full customer transactions table. But I'm also going to build out a micro table that includes 2,000 customer transactions. This will let me show performance differences across 3 different sizes of table, and we'll see how the apply operator fares in each. Now let's take a look at our 3 contestants in today's performance showdown. What I want to do is get the latest customer transaction for each customer, and to do so, I have a variety of techniques. I will let you know up front that cursors and while loops will be slower than the other options, so they're off the table immediately. Instead, I'll focus on 3 set-based solutions. The first one, I think, is the option most people will think of when you ask for a solution to this problem. We start with customers and join to customer categories, then to people. After that, we perform a left outer join. This join connects us to the customer transactions micro table. From this table, we want to retrieve all customer IDs, as well as the maximum customer transaction ID for that customer. I'm using this as a proxy for transaction date. It turns out that the customer transaction ID increases monotonically with respect to the transaction date. That is, when the transaction date increases, customer transaction ID also increases. For this reason, I'm able to use the ID as a proxy. If I couldn't, this query gets a lot more complicated. Anyhow, I have the customer ID and the latest transaction ID. But if we look at the select clause for a moment, we can see that I also need the transaction date, invoice ID, and outstanding balance. Those are things I don't have from my subquery, so I need to join to the customer transactions micro table a second time in order to retrieve them. Contestant number 2 is an approach that will make intuitive sense if you are familiar with window functions. In this case, we are going to build a common table expression that I'm calling transactions. This common table expression will go through each of the rows in the customer transactions micro table and retrieve all of the columns we need. It will also use the row number function, partitioning by customer ID and ordering by transaction date, descending. What this gives us is, for each customer ID, we will get a value of 1 for the record with the latest transaction date. The next will have a value of 2, and so on. Then, in our base query, we start with our 3 starting joins of customer to customer categories and people. Then we left outer join to the transactions CTE, joining on customer ID and only bringing back the record where the value for row num is 1. That is, we're only going to retrieve the latest record for each customer, just as we wanted. The final contestant in this race is the apply operator version. We'll use an outer apply because not all customers will have orders in our micro table. For each customer, we will generate an ad hoc function that queries the customer transactions micro table and retrieves the top 1 record based on transaction date descending. If I run these in VS Code, we'll see that I do generate result sets for each. You can check those result sets for your own if you'd like, but I will assert here that the 3 queries do return the same results and they are functionally equivalent queries. If you're willing to believe me on this, we can move on to Plan Explorer. If not, I recommend pausing the video, trying it out for yourself, and then catching up with the rest of us. In Plan Explorer, I already have a new plan window ready to go. I'll paste in the code to create my temp table, add the index to it, and then run each of the 3 queries. We'll ignore the first couple of rows in the statements list and focus on the 3 query variants. In my pre-recording testing, the subquery version took 6 milliseconds of wall clock time and 4 milliseconds of CPU time, as well as 152 reads. The window function version took 3 milliseconds of wall clock time and 3 milliseconds of CPU time, as well as 68 reads. The apply operator version took 2 milliseconds of wall clock time, 2 milliseconds of CPU time, and a whopping 1,689 reads. I think it's fair for us to say that the apply operator variant is the worst of the bunch here, but let's briefly look at the execution plans to see what's actually happening. Drilling into the subquery plan first, I'll focus on the part of the plan that differs. The joins from customers to customer categories and people will remain the same across all 3 query variants, so there's nothing interesting in that part of the plan. Instead, let's take a look at the top part of the plan. We have our set of customers and then the hash match to customer transactions micro. But before we perform the hash match, we perform a hash aggregate of transactions. Thinking back on the query, this was the left outer join to the customer transactions micro table where we found the max transaction ID for each customer ID. That gets us from 2,000 rows down to 233, as there are 233 unique customers in this micro table. But then we need to perform a second scan of the customer transactions micro table, pulling in all 2,000 rows a second time before hash matching against the rest of the data. This nets us 735 rows. Because we have 2 scans of the transactions table, it's not the most efficient answer, but from the standpoint of CPU utilization, it's not bad. And if I mouse over the select node, we can see that SQL Server requested approximately 5 megabytes of memory to execute this query. Moving on to the window function variant, our query is simpler. We perform 1 scan of the index we created on the transactions table. Then we run through a sort, segment, and sequence project combination that tell us a ranking window function is in our T-SQL code. We then have a filter node that converts the 2,000 rows we processed down to 233 rows. We join those 233 rows to the 735 customers and return back the results. As we already saw, this variant requires fewer reads because we are only scanning an index rather than the full table, and we are only doing this once instead of twice. If I mouse over the select node, our memory grant is just over 4 megabytes, so that's smaller as well. And finally, we have the apply operator variant. Here we see the ordering of our execution plan flip a bit so that the hash match of customers, people, and customer categories happens first. Then we have a nested loops join. One thing you'll see quite commonly in plans using apply is a push toward nested loops joins. It's not a guarantee that the optimizer will use a nested loops join whenever you have the apply operator in a query, but it's a pretty safe bet. In this case, we have 735 people. For each of the 735 people, we engage the top operator to stream the top 1 result from the customer transactions micro temp table. Each operation necessitates an index seek, and we can see that 233 of the 735 people have orders, but we need to look for each one of them to make sure. These 735 index seeks is why we have 1689 reads, well above all of the other two plans. In those plans, we performed either one or two scans of the customer transactions micro table, and that table is quite small. Keep that thought in mind as we'll come back to it soon. If I hover over the select node, our memory grant is the smallest of the bunch at approximately 2.5 megabytes of RAM. Recapitulating what we've seen so far, there's not a significant difference in either CPU cost or duration. The window function has the fewest reads, and the apply operator has by far the most. The subquery and aggregate solution has the largest memory grant, followed by the window function, and the apply operator has the smallest. With this in mind, I'd like to posit something. What we noticed here is that two of our query plans performed scans of the customer transactions micro table. The apply operator, meanwhile, pushed for a series of seeks. If we keep the number of customers fixed at 735 and increase the number of records in the transactions table, assuming that the execution plans for these three techniques do not change, there will come a point in which 735 seeks beats one scan. With that in mind, let me switch to the next script. This one goes against the customer transactions table. Just to give you an idea of how many rows there are here, let's run the query. We have 882,282 rows in this table, a far sight above the 2,000 records we had before. My three queries are fundamentally the same, except that we are querying against the customer transactions table rather than the micro-sized temp table we created before. And as a quick note, the reason I'm not going to show you the small variant of this is that you're actually going to see basically the same results between small and this full-sized version. So to save a little bit of time and effort, I decided to skip that midpoint where you'll see the transition, and we'll just show the largest version. So as such, let me copy these and bring them into Plan Explorer. In a new window, I'll paste these new queries and then select Get Actual Plan to execute them. Let's give them a chance to run, and oh, how the turntables have turned. Let's take a look at these three plans and see whether the apply operator can start its victory lap. In my pre-recording run of these, the subquery with aggregation took 263 milliseconds to run, including 237 milliseconds of CPU time. The window function took 725 milliseconds of wall clock time, with 689 milliseconds of CPU time. And the apply operator version took 9 milliseconds, including 9 milliseconds of CPU time. That is 2 orders of magnitude better. Looking over at the I/O side of the house, we can see that the subquery with aggregation has the most I/O, and that the apply operator is not considerably different from the window function in terms of number of reads. Now let's peek at each query and see how its execution plan has changed with a large dataset. Our first go involves the subquery with aggregation, and it starts with a scan of the customer transactions table. We aggregate the data by customer ID, getting the maximum customer transaction ID for each customer. We scan 882,000 rows and get back the max transaction ID for the 335 customers who have transactions. To that, we perform a nested loop join back to the customer transactions table, picking up the transaction date. Interestingly, it's using the primary key and then a key lookup to retrieve the other columns rather than using our purpose-built index. Finally, we hash match to the 735 customers and return our results. Mousing over the select operator node, we see that the memory grant was just shy of 4 megabytes. Next up, we have the window function, and it starts similarly to the apply operator. We hash match customer categories, customers, and people. But then we feed all of that into a sort operator, sorting by customer ID ascending. This sort operation opens up the possibility of a merge join, which requires both sides be sorted. Let's scroll down and check out what we're merge joining. In here, we see a scan of the customer transactions table using the index we built for the task. We then have a very expensive sort operator with a yellow exclamation mark. If we hover over that, it tells us that we spilled over into tempdb, meaning that our sort contents did not fit into memory. From there, we have the standard window function segment and sequence project. We perform a compute scalar operation to get our columns in the appropriate condition and filter down the records with a row num of 1. Mousing over the select node, and we have a memory grant of a whopping 75 megabytes, considerably higher than what we had before. Now let's look at the apply operator. It turns out that our execution plan is exactly the same as before. The shape of the plan, exactly the same, and we can see just how efficient it is. We read a total of 335 records from our 735 outer loop operations and join those together. Mousing over the select node, our memory grant is basically the same size here as it was with the smaller dataset. This is a very efficient plan at these data sizes, and as I'll explain in the outro section, it only gets better relative to alternative methods of querying as our customer transactions table gets larger. Now let's go back to VS Code and genericize the problem. Instead of getting the top 1 record, we can get any arbitrary number of records back. I now have 3 more queries. In this one, I want to get, for the last 5 invoices, a basic number of aggregations, telling us the number of invoices, the number of invoice lines, the totals of quantity, extended price, tax amount, and total profit. I have 3 different ways of writing this query, and I'm going to start with the larger tables to save us some time. The first version of this query uses a correlated subquery. We have our initial joins of customers to customer categories and people. Then we want to join to invoices and invoice lines. In the where clause, I have a correlated subquery that gets the top 5 invoices for that customer ID based on invoice date descending. Because I have aggregate functions and non-aggregated columns, I wrap this up with a group by and include the non-aggregated columns. The second variant of this query uses a window function inside of a common table expression. We will partition the invoices data by customer ID and order by invoice date descending. In addition, I'll include the customer ID, invoice ID, and invoice date. In the main query, after our initial table joins around customers, customer categories, and people, we left join the invoices common table expression based on customer ID and include only the records with row num less than or equal to 5. That is, we will get at most the 5 latest invoices. If this customer has fewer than 5 invoices in total, we get as many as are available. Then we join to the invoice lines table and get all invoice lines associated with those invoices. Once again, we have non-aggregated columns and an aggregation function, so we need a group by clause to sort that out. Finally, we have the apply operator variant. We use outer apply here and retrieve the top 5 invoices based on the customer ID and ordered by the invoice date. The query is otherwise very similar to what we saw before, so I won't belabor the point any further. I will also, for the sake of brevity, assert that the outputs for these 3 are identical and instead take the query right to Plan Explorer. Let's open up one more plan window and see how the 3 variants fare. We can see a fairly drastic difference between these 3 queries. The correlated subquery variant, when running this prior to recording, took 3.5 seconds to complete and needed 2,217,771 reads to complete. That's a lot of database power for a single query. The window function version needed 475 milliseconds of wall clock time and 5,267 reads. Meanwhile, the apply operator blew both of them away, needing 26 milliseconds of duration and 14,778 reads. Let's quickly look at the 3 query plans and see how they look. For the correlated subquery plan, let's start down and to the right a bit, sort of like a reverse Zapruder film. After our traditional joins of the customers, customer categories, and people tables, we have a hash match join to the invoices table, pulling in all 666,906 invoices. Then we have a wild nested loops join to the invoice lines covering index that retrieves 3,327,180 total rows. There's a filter operator that returns back just the 3,675 rows that we care about. We then need to retrieve all of the invoice lines, perform a hash match to join these together, and then aggregate our results to get back the 735 rows we expect, one for each customer. Checking out the memory grant, we need an absolutely wild 2 gigabytes of memory just for this one query. A few copies of this query running at any given time can put a serious hurt on your average SQL Server instance. The next variant, which uses a window function, is a lot more sane. In this case, we have an index scan of our 666,906 invoices. We then sort these and perform a window aggregate to calculate those partitions. Eventually, we filter these down to the 3,675 invoices that we care about. From there, we hash match to the invoice lines table, but we still need to perform a full index scan, pulling in 1,753,051 rows. This gets us to 8,019 invoice lines, which we aggregate down to our 735 customers, join to the customer table set, and return to the end user. This has a memory grant of approximately 240 megabytes, so roughly one order of magnitude better than the correlated subquery version. Finally, our apply operator version looks much nicer than the others. We start with the fluff around customers and then perform a nested loop join to get invoices. We get at most 5 invoices per customer, so we seek against the invoices table 735 times, returning a total of 3,675 rows. We then sort these and perform another nested loops join to the invoice lines table, giving us the 8,060 rows we need. From there, we aggregate the data and return 735 rows to the user. My memory grant is also an order of magnitude smaller than the window function version, needing approximately 13 megabytes of RAM. Even though the window function version of this query did not need to read quite as many pages as the apply operator version, we needed an order of magnitude more RAM and CPU to accomplish the same task, so I can comfortably declare the apply operator version to be the winner here. Now let's travel to the classroom so I can explain the theory behind what we've seen here. Welcome back from the demo. We were able to see that the apply operator sometimes performed better than alternative formulations, but not always. In this last segment, I'd like to explain when apply is likely to do better and when you should probably stick with another alternative. To do so, let's head to the classroom. There are a few takeaways I want to discuss from our demo. The first thing I want to note is that the apply operator typically generates nested loop joins, based on the consideration that we run an ad hoc function once for each element on the left-hand side. As such, if there are 20 rows on the left-hand side, we'd almost assuredly want 20 nested loops joins rather than 20 hash matches or 20 merge joins. Thus, let's talk about what makes for an ideal scenario for us to use the apply operator, given that we want to perform a nested loops join. That is a nested pair of for each operations, where the first level iterates over each element on the left-hand side, and the second level iterates over each result in the ad hoc function. The first consideration we have for an ideal use of apply is that we have relatively few records on the left-hand side, or what I've been calling the parent records. If I have a billion rows, that means a billion iterations of my outer loop, and that's probably not going to perform well. The smaller, the better here. Second, we want a huge number of rows in the table or tables we reference within the ad hoc function. We could consider this the child records. If I want to get transactions for each customer, I want a relatively small number of customers, but a huge number of transactions. The third consideration, which is critical here, is that I want relatively few interesting rows to come out of my ad hoc function. In other words, we might have a billion customer transactions, but I'm only interested in the latest one for each of my 735 customers. Thus, I'm interested in 735 out of a billion rows. In other words, let's take a quick peek at this execution plan. In this example, I have 19,119 customers. For each customer, I am getting the latest sales order, so I will retrieve 19,119 records. If the sales order table has 20,000 rows, I'm retrieving each row one at a time, and that's not a good outcome. By contrast, if I have a million rows in that table, I'm retrieving 1.9% of the rows. And that leads me to a rule of thumb when it comes to SQL Server index efficiency. Many people will say that you want to avoid index scans and perform index seeks instead. This advice is not always prudent, and the reason comes down to how indexes behave. This is a very simple diagram of how SQL Server lays out indexes on disk. The bottom level of the index contains our data, and the higher levels contain pointers. The number of levels we have depends on how many rows we have in the table and how large the key is, so don't take 3 as some magical number of levels. Each leaf level page is also implemented as a doubly linked list, so we can navigate from a page to its prior page or its next page. Knowing this, let's talk about scans versus seeks. An index scan has us navigate the top level and relevant intermediate levels until we get to our starting point. Then we start at that page and continue reading until we've pulled in all of the information we need to resolve a query. Scans are not inherently bad. It's the best way to get a lot of data. The point when scans become bad is if we are performing a scan when there is a more efficient alternative. By contrast, a seek behaves differently. With each seek, we start at the top level and navigate through each intermediate level. We end up on the single page that contains our data and retrieve our data from that page. As you can imagine, if there are a huge number of leaf pages and we only need to retrieve one row, a seek will be considerably more efficient than a scan. But each seek requires us to traverse that top level page and any intermediate levels. So if we perform a large number of seek operations, we perform more read operations than if we simply scan through the pages. This is especially true if we read all or nearly all of the pages in the process of our seek operations. As a quick aside, I do want to point out that SQL Server does have some optimizations where it will say, I am performing an index seek, when really it's actually performing a range scan over a relatively small range. That's a little bit aside from the point here, so I did just want to mention that so that the people who are going to be pedantic in the comments will at least be able to understand that I do understand this. Nonetheless, you're still welcome to be as pedantic as you wish in the comments. Go for it. Anyhow, back to my story. So for this reason, we have a cutoff point. Below this point, we want to seek. Above this point, we want to scan. The cutoff point I'll show you is, as I mentioned, a rule of thumb. We can quibble with the exact numbers, but I think it's a pretty solid starting point, and it does play out well when it comes to the apply operator. In general, if you need to retrieve 20% or more of the rows in a table, a scan will be more efficient than equivalent seeks. If you want to retrieve less than 0.5% of data, a seek is more efficient. The in-between spot is more of an it depends zone, where sometimes you may find scans to be more efficient than seeks, but change the criteria slightly and, well, the better technique to use becomes seeks instead of scans. This ties back really well with our rules from before. If we have a huge number of records, but we're only interested in a tiny percentage of them, that sounds exactly like the kind of behavior we want with index seeks. And the apply operator pushes the optimizer to bias toward performing index seeks. Thus, the apply operator works particularly well when we want to push the optimizer to seek instead of scan. By contrast, think of the opposite of these rules. If we need to perform a table scan of the child table for each parent record, that's going to fare poorly compared to one table scan. If the number of parent rows is huge, that's going to make the outer loop in our nested loops join more expensive. And if you need to retrieve almost every record from the child table to satisfy this query, or even if you need to retrieve 20% or more of the records from the child table, then the apply operator would be a bad choice for the job. Query tuning has quite a bit of intricacy to it, but it's not magic, and hopefully I've helped to clarify one small part of it in this video. In the next video, I'm going to show you how you can simplify calculations using the apply operator. We'll have links and show notes in the description below, and until we see each other in the next video, take care.